on. So this is our lube pack, which is the lubrication system for our turbine. We have a lube oil sump, a lube oil pump. This bladder accumulator is a backup source of oil pressure in case we have a power failure. There's a bladder inside here with a certain nitrogen pressure inside it. If we have an oil failure and our pump stops, the bladder will expand and will, for a certain amount of seconds, will continue to push oil through our system, which gives our turbine enough time to run down. So it's just an emergency supply of oil pressure. We have a lube oil switch, which is tied to the trip valve. It's an interlock. Without lube oil pressure on the switch, we will not be able to open the main process air valve to the cold box. You can see some other basic components. There's an oil filter here. There's a seal gas demister. There's an oil cooler. There's also an oil heater at the back of the sump. This lubrication system requires seal gas to prevent the lubrication oil breaking through from the bearing housing into the process air. So we use instrument air from the beds that we use as seal gas. We have a seal gas pressure switch here, which monitors the seal gas pressure, and if we do not have sufficient seal gas pressure above a certain set point, it will not allow our oil pump to run. So we need seal gas pressure in order to run the oil pump, and we need oil pump running and oil pump pressure in order to open the trip valve to the plant. Okay. We have a seal gas pressure regulator down here, and we have a gauge where we can see our seal gas pressure, and we've got a flow meter. We can see the flow of seal gas to the turbine bearing. This cold box purge FM544, we take a small amount of waste nitrogen from the cold box and we feed it into the actual insulated cavity of the cold box around the column itself, and that will just that dry nitrogen purge just helps to prevent the ingress of moist air into our actual cold box housing and keeps it dry. If we had water vapor going in there, the water vapor would freeze and eventually would end up with wet insulation. Our process air will enter our cold box through the process air line via the main trip valve, and we have the air moving down through our main heat exchanger, and we then have a split of the process air. The one leg will lead to the turbine. It's what we call our refrigeration or our liquefaction loop. The air will move to the turbine, be expanded through the turbine, and create extreme cooling. That stream will then move back up through the same heat exchanger and will be recycled back to our air compressor inlet filter suction. Okay. The second split, the second leg of the split, will be process air, which will continue down through the main heat exchanger. Because it's moving in opposition to the cold stream coming up through the heat exchanger from our turbine, that high pressure air, by the time it leaves the main heat exchanger, becomes partially liquefied and is fed into the bottom column or our nitrogen column. Okay. So that whole process is controlled by the valves on the cold box face. We have on our turbine leg, on our liquefaction leg, we have V530, which is the main turbine valve. We need to open that in order to open that leg in order to spin the turbine. It's a manual valve. On the process air split that leads to the actual column, the high pressure leg, we have PCV 511, pressure control valve 511, which is an automatic control valve which will control the process, which will control the pressure of the bottom column. In doing so, it controls the flow of air to the bottom column. And this is automatically controlled according to a set point in our PLC. All right. So the liquid that moves into our column then forms the basis of a distillation process between the two columns. We have a lower column, a nitrogen column, an upper column, an oxygen column, and they are thermally linked by a heat exchanger known as our reboiler condenser. They're also linked by certain air lines and liquid lines, gas lines and liquid lines, such as our crude feed line, our pure nitrogen feed line. So we control that distillation process with these valves. The liquid level in the bottom of the nitrogen column is known as our crude liquid. It's a crudely distilled liquid, which is a higher oxygen purity than air, but it's nowhere near as pure as the liquid oxygen product we would like. This valve, our level control valve 520, our crude level control valve, controls the liquid level of crude in the sump of the bottom column. And as that liquid rises, as the liquid level rises, the valve will open more to maintain a certain set level. The level of the liquid in the crude is monitored by LT 520, level transmitter 520, which will give a feedback to the PLC to give us an indication of the level, and thereby allowing us to control this level. Likewise, the level of oxygen in the top column will be controlled by LCV 530, and we have LT 530, which monitors our oxygen liquid level. As the liquid level rises, LCV 530 will remove more liquid, thereby maintaining, and this is our oxygen product valve. At the same time it's controlling the liquid level, it's also controlling how much oxygen goes to our tanks. Okay. We then have two manual valves, V556 and V550. V556 is our nitrogen product valve. It's a manually controlled product valve, and we will remove as much nitrogen as we can during nitrogen mode. We will remove as much nitrogen as we can using this valve without compromising nitrogen purity. V550 is what we call our pure liquid feed. It's a line that takes pure liquid nitrogen to the top of the oxygen column. It's only open during oxygen mode, and we use that pure liquid feed as a cold seal at the top of the oxygen column to prevent excess oxygen molecules escaping into the waste. That cold liquid nitrogen injected into the top of that column acts to condense any oxygen gas molecules that may be making their way up and into the waste stream. So they condense and they fall back down as reflux for that column. Okay, you'll also see that we have pressure transmitters. We have a turbine inlet pressure transmitter and a turbine outlet pressure transmitter. If ever these pressure transmitters need to be exchanged, if they become faulty, always be sure to check the range written on the actual transmitter itself, because if you fit a replacement with the wrong range, obviously the PLC will give an incorrect reading. Okay. Our sample lines, we have an analyzer which will analyze our purity of our oxygen and our nitrogen products. And our samples, our cold box samples, come from here and are fed through to our analyzer. You'll notice that we have a nitrogen sample and an oxygen sample. It's fairly obvious. We're producing nitrogen and oxygen. We want to know what the purities of the product are. We also have V501, which is an instrument tap, and that is actually a sample that comes directly from our waste line. So we can open up that line and we can use the same analyzer to monitor the oxygen purity, the percentage of oxygen in our waste line. Now, why we would want to do that, we would want to do that during oxygen production mode, because in oxygen production mode we want to keep as many molecules of oxygen inside our distillation process as possible. We don't want to be expelling excess oxygen through our waste. So we can look at our waste purity, and if we see that our waste purity is too high, we can then adjust our PL feed to condense more oxygen and reduce that wastage of oxygen. That would be during oxygen production. During nitrogen production, we want to keep as much nitrogen molecules in the distillation process. We only want to lose nitrogen molecules as much as possible through the product line. So we will have the PL valve closed, 100% closed during nitrogen production. The other thing you can see on our cold box is V552. That is our gaseous oxygen vent. During oxygen production, That valve would normally be closed, as I said, to keep in as much oxygen as possible. But during nitrogen production, we have that valve regulating a flow of oxygen from just above the reboiler condenser where our oxygen is boiling, and that will get rid of excess oxygen from our process during nitrogen production. So these are our product lines coming directly from the coal box, and you'll see that each product line, the nitrogen product line and the oxygen product line, has two valves and two possible routes for the liquid to move through. The bottom two valves are product valves for nitrogen and oxygen, and the top two are dump valves. So our PLC will have a certain set point for purity. If, say, we're running oxygen production, and if the purity of the product that is being measured from our sample line by our analyzer falls below a set point, a purity set point, the PLC can automatically close the product valve, open the dump valve, and divert product, instead of going to the tank, to a vaporizer where it'll be vaporized to atmosphere. Okay, so that's for both of those. We also have a pressure relief valve here in case, for some reason, both of these valves are closed and we have liquid trapped in the line. We have a pressure relief valve that can open to release excess pressure. This manifold here is just an instrument air manifold and solenoid control for these two valves. So these solenoids will be controlled by the PLC. We'll get digital signals from the PLC to allow instrument air to flow to whichever valves need to be opened and closed. And on the base of the coal box here, you can also see that we have drain valves next to our product valves. We have 4 drain valves, and these would be used in circumstances such as when we're thawing the plant. We would open up all our drain valves and blow dry air through the entire column and out the drains. If we were going to shut down our plant for maintenance and we had a column full of liquid, we could also open these drain valves and drain liquid out. These drains all drain through a vaporizer outside, so we could vaporize all the liquid in the plant. If you have an emergency situation where your liquid level is too high for whatever reason, maybe your level transmitter failed and you suddenly discover that you have high liquid levels, you can open up the reboiler drain level or the crude drain level to drain liquid in an emergency situation as well. Just a quick point about starting up our turbine. As you know, we have a manual valve which will allow pressurized air to come through our turbine refrigeration loop. When we start up a warm plant, a plant that hasn't been running for a while, or a plant when we're first commissioning it, the process air will be very warm and it'll have energy. It'll have more energy than cold air. So we would very, very gradually open up our turbine valve and allow our turbine speed to come up, and we would control our speed with that valve. As the plant begins to cool down and our expander loop begins to cool down the incoming process air stream, the air going into the turbine is going to be colder and colder, less energy, so the turbine will start to slow down. By the time you get to running the plant, making liquid in normal production, the turbine valve will be 100% open. So our turbine loop, generally with a stable running plant, will be 100% open, and the pressure control valve will be controlling the split of air going into the column. All right, so very, very basically, that split of air is very critical in terms of running the plant, because the two loops have two different functions. The turbine loop, the only function of that loop is to create cooling of the process airstream and create liquefaction. So the more we split air towards the turbine loop, the more liquefaction we're going to get, the more product, in a very basic way, we are going to make. The more air that we put to our column, again in very simplistic terms, the more air we put to our column, the more molecules are going to be going into the distillation process. The molecules which flow through the turbine do not enter the distillation process at all. They are merely a cooling stream used to cool, and then they recycle to the compressor. So very simplistically, what we aim to produce as much liquid as possible by putting as much to the turbine loop as we possibly can. But if we put too much to the turbine loop, we will begin to compromise purity. We'll begin to lose purity because we won't have enough molecules in our distillation process. So we want to keep a balance between those two, putting as much to the turbine as possible, but still enough to the column to have good purity of product. So we do that with our turbine valve 100% open once the plant is cold. We do that by regulating this valve and regulating the set point of this automatic valve. If we find that we are producing very high purity product, we know that we can reduce our column pressure a little bit as we reduce pressure control valve 511. As we reduce our column pressure, what we're essentially doing, we're closing down the column, we're putting more gas flow through to the turbine loop. We will begin to make more liquid. If we find we're having a problem with purity, we just cannot get oxygen or nitrogen purity, it's probably a good indication that you're not getting enough process air making its way, liquefied air making its way into the columns. So we can try to raise our set point on our column, put more air and liquid to the column itself, and thereby help our purity. Obviously, if you have got lots of air going to the column and you are pulling out lots of nitrogen product in nitrogen mode, if your nitrogen product valve is wide open, at some point you're going to begin to lose purity because you are taking too much nitrogen out of the plant. So in nitrogen mode, if you are battling to find a good purity, you can do two things. You can increase the air to the column, and you can reduce the draw of nitrogen product, keep more nitrogen molecules within the distillation process, and therefore allow your purity to come back up. In oxygen mode, the level of the oxygen bath and therefore the level of the amount of oxygen being drawn out of the column is automatically controlled. So we don't manually control that in the way we do in nitrogen mode. In oxygen mode, if you're struggling to find purity, generally you would put more air to the column to allow your purity to improve, and you would monitor your waste purity and control your pure nitrogen feed to bring that waste purity down. In other words, to prevent too much oxygen escaping from the waste. Generally in our waste stream, we would like to have about 3.5% oxygen molecules or less. So if we're finding we've got 8% oxygen in our waste stream, we can open up our PL feed, this is in oxygen mode, and trap more oxygen, condense it, and reduce the loss of oxygen from our column, and that will help our purity.